Welcome. Today, you and I are going to go on a journey together through one of the most elegant, most powerful theorems in all of calculus. Green's theorem. Before we can appreciate Green's theorem, we need to remind ourselves of something. What is a line integral? Imagine you have a curve, let's call it C, drawn on a flat piece of paper, like a path through a park. Now imagine a force field everywhere in that park. That total work is exactly this integral p dx plus q dy, summed all the way around the path. Now, if the curve is complicated, and p and q are complicated, evaluating this directly can be extremely painful. And that is precisely why Green's theorem exists. Here is our question for today, and it has two parts. Part A asks us to state the theorem and show its proof. Part B asks us to evaluate this integral all the way around the curve C, which is the unit circle, x² + y² = 1. Now, Part A. Let us state Green's theorem properly. Before we write the formula, there are 4 conditions that must be satisfied. Condition 1. C must be a simple, closed, piecewise smooth curve. Condition 2. C must be positively oriented. This is important. If you go clockwise, your answer gets a minus sign. Condition 3. D is the region enclosed by C, the area inside the curve. Condition 4. P and Q must have continuous partial derivatives everywhere inside D. When all 4 conditions hold, the theorem says this. The line integral around the boundary C equals the double integral over the interior region D of this expression. Partial q over partial x minus partial p over partial y. Instead of walking around the boundary doing difficult work, we look inside, we compute something about the interior. And they are equal. That is the magic of this theorem. Now the proof. The whole strategy is this. We do not try to prove everything at once. Instead, we split the theorem into 2 smaller, easier claims. Claim 1 says, the p dx part of the line integral equals negative the double integral of the partial derivative of p with respect to y. Claim 2 says, the q dy part equals the double integral of the partial derivative of q with respect to x. And here is the beautiful part. If we add claim 1 and claim 2 together, the left sides combine into the full line integral of p dx plus q dy. The right sides combine into the full double integral. And we have Green's theorem. So all we need to do is prove each claim independently. Let's go. Let us prove claim 1. Look at our region D. For a vertically simple region, and our disk is certainly 1, every vertical line you draw through D enters at a bottom boundary curve. Now look at the inner integral. We are integrating the partial derivative of p with respect to y, and just like that, claim 1 is proved. Claim 2 is proved in exactly the same spirit, but this time we integrate in the x direction. And again, accounting carefully for the direction of travel along C, this gives us exactly the line integral of q dy. Claim 2 proved. We add claim 1 and claim 2 together. On the left, the double integral over d of partial q over partial x minus partial p over partial y dA. On the right, 2 double integrals with the same region, they combine into 1. Now let's move to part B, our actual problem. We have the unit circle, x² + y² = 1. It is simple, it is closed, and it is traversed counterclockwise, positively oriented. Every single condition for Green's theorem is satisfied, so we are allowed to apply it. We replace the line integral, the hard one, going all the way around the circle, with a double integral over the disk D. The very first thing we do always is identify p and q from our integral. So p is the expression that is multiplied by dx. Look at our integral. What sits next to dx? It is 2x³ minus y³. So p equals 2x³ minus y³. Q is the expression that is multiplied by dy. What sits next to dy? It is x³ plus y³. So q equals x³ plus y³. Now we compute the 2 partial derivatives that live inside Green's theorem. Q is x³ plus y³. When we differentiate with respect to x, we treat y as a constant. The derivative of x³ with respect to x is 3x². So partial q over partial x equals 3x². Now the second one. The partial derivative of p with respect to y. P is 2x³ minus y³. The derivative of 2x³ with respect to y since x is now the constant, is 0. The derivative of negative y cubed with respect to y is negative 3y squared. Now we differentiate with respect to y, treating x as the constant. So partial p over partial y equals negative 3y squared. These two results are our ingredients. Now we form the expression inside Green's theorem. We substitute what we just found. 3x squared plus 3y squared. We can factor out the 3, and our double integral becomes 3 times x squared plus y squared over a circular region. Here comes the clever move. The substitutions are x squared plus y squared equals r squared. That is just the Pythagorean theorem in polar form. And notice, our integrand is exactly 3 times x squared plus y squared, which means it becomes simply 3r squared. Now the area element. In polar coordinates, a tiny area patch is not dx dy. It is our dr d theta. That extra r is important. It accounts for how the patches get bigger as you move away from the center. Now we evaluate. The rule with double integrals is always inner integral first, then outer. Inner integral. We integrate 3r cubed with respect to r, from r equals 0 to r equals 1. The antiderivative of 3r cubed is 3r to the power 4, divided by 4. The inner integral gives us 3 over 4. Outer integral. Now we integrate 3 over 4 with respect to theta, from 0 to 2 pi. 6 pi over 4, we cancel the common factor of 2, gives us 3 pi over 2. And there it is. The answer is 3 pi over 2. We started with a line integral that had cubic terms, 2x cubed, y cubed, x cubed, going all the way around a circle. If we had tried to evaluate that directly, we would have needed to parameterize the circle as x equals cosine t, y equals sine t, substitute everything in, expand the cubes, and integrate over a full period. It would have been messy and long. Instead, because we recognized Green's theorem could apply, we converted the problem. Before we close, I want to leave you with something practical. Something you can take with you. Here are the 5 steps every time. Step 1. Identify p and q. P is next to dx. Q is next to dy. Step 2. Compute partial q over partial x, and partial p over partial y. These are your two derivatives. Treat the other variable as a constant each time. Step 3. Subtract partial q over partial x minus partial p over partial y. Simplify the result as much as you can. Step 4. If the region is a circle, switch to polar coordinates. Remember x squared plus y squared becomes r squared, and it becomes our dr d theta. Step 5. Evaluate inner integral first, then outer. Be careful with the limits. Follow those 5 steps faithfully, and Green's theorem will never defeat you. For our problem today, the answer was 3 pi over 2. A very useful friend that saves you a lot of calculation time. If this helped you, please like the video, share it with who is studying the same topic, and subscribe so you never miss another explanation like this. See you in the next one.